Simple microscope. Any idea what a simple microscope is? Have any of you seen a simple microscope?
Yes, sir.
Where? What does it look like?
Sir, biolab.
Biolab. That is not a simple microscope. Biolab, you must have seen microorganisms or cells. Those are not shown by simple microscope.
No, sir. It's the one which has like those two things. Then you look under it and
Wait, repeat.
it has two parts to it. When we look, there's like two parts to it, which I don't know the labeling and the parts, sir. Well,
So you are saying one of them is simple microscope.
no, sir. It is a part of the simple microscope. Like you can keep shifting what to see over there, but like the magnification is like not much on it. Not as much as like 100x or something. It's like 5x or something.
Okay, okay. Fine, fine. Pradyun is saying a single lens. Yeah, single lens. What kind of single lens? Magnification should be there. So diverging. Diverging does not magnify. Diverging lens, which is basically a lens of negative focal length. Yeah, it makes diminished images. We want enlarged image, so it's a converging lens, positive focal length. Okay, so it should be, if you are using it in air, it should be a convex lens, basically a magnifying glass. Okay, that is what is a simple microscope. I'm sure you all must have used a magnifying glass to read enlarged letters or maybe burn something. Okay, so simple microscope is nothing but a magnifying glass. Pradyun is asking, but the object is placed between focus and optical center, right? Yeah, we'll come to that. Yeah, object should be present between the focus and the optical center. Correct. Okay. So see, imagine reading something through a magnifying glass. Obviously, what you see is the image of the letters. You don't see the letters directly when you see through the glass. Refracted light only will enter into your eye, no, when you see through the glass. So you are seeing the image. So when you try to read something using a magnifying glass, I don't know how many of you have tried this. If you keep the glass close enough to the letters or within a certain distance from the letters, only then you will be able to see magnified letters and upright letters, proper orientation. If you bring the magnifying glass too far from what you're trying to read, you will see inverted images, inverted letters. Okay, so only up to a certain range of distances you can expect magnification with upright image formation. Anyway, we want an upright image, means erect image. And magnification also should be there. Now we have discussed all cases of image formation by lenses. Fine. Okay, fine. I think I asked you to draw those cases. Okay, let's take this for example. One of you tell me if object is beyond 2f, okay, from a convex lens. If object is beyond 2f from a convex lens, where does the image form? Image forms between f and 2f. Okay. And if image is closer than the object, let me show you all cases of image formation basically. You must be very comfortable with this, only then you can answer questions based on optical instruments clearly. Okay, let's say these points are marked F to F. If object is beyond 2F, basic ray tracing, one ray parallel to principal axis. Passes through the focus on the other side. And the other ray directly through the optical center. Passes without any deviation. They meet here. This is where the image forms. So if this is the object, this is the image. So if object is beyond 2F, image forms between F and 2F, and you get an inverted image. And it's diminished also. It's real because light, refracted light, is actually passing through the image position. It's a real image. So is this what we want a simple microscope to do? No. Suppose the object is between F and 2F. Consider an object like this between F and 2F. Then again, basic ray tracing. One ray parallel to principal axis should pass through the focus. Another ray directly through the optical center, passes without any deviation. And these two rays meet somewhere here. This is where the image forms. Enlarged image. Good, but it is inverted. Okay. And also, see, if you just want enlarged image, then you can use this case. You can use a convex lens and ensure the object is between F and 2F. Then you will get image on this side. But there's a problem with using this lens. See, image forms here, that's okay. But if you want to see this image, then your eye should be at a distance of 25 centimeters further away. Only then you will be able to clearly see this. That is the problem in using this. Okay. And also another problem is you see inverted images. Okay. We are not comfortable seeing inverted images. We want upright images. Okay. So this case also cannot be used for a simple microscope. Okay. I'm not saying there is no magnification. There is magnification. There is enlarged image being formed. It can be seen also if you are at a sufficient distance. Okay. But that is not what we want a simple microscope to do. Next case. If object is within the focal length, say somewhat like this. Again, basic ray tracing, one ray parallel to principal axis passes through the focus. Another ray through the optical center passes without any deviation. These two clearly will not intersect after refraction. They are diverging, so they won't intersect after refraction. But if the eye is on the right side, then these rays will appear to be entering into the eye from somewhere back here. Just extend them in the backward direction. This is the common point from which they appear to be coming. So this is the image position for this object. So we get an upright image, we get an enlarged image, and seeing this is much more easier actually. See, the image is already formed at a certain distance from the lens, no? Then your eye will only need to be a little further away from the lens to be able to see it. Okay, total distance should be at least 25 centimeters. Okay, then you will be able to see it. So this is the best case for a simple microscope, and this is what we make use of. But remember, for this kind of image formation, one of you tell me, where should the object be? Okay, Pradyumna has already told anyway. It should be, the object should be between the focus and the optical center. It should be within the focal length of the converging lens. Only then we can get an image of this kind. Okay. Now, when it comes to a microscope, what we are interested in is magnification. Okay, this is where you all need to be careful. Let's discuss magnification of a microscope. Usually, okay, one of you tell me, what is the definition of magnification? What is the basic formula for magnification?
That is the enlargement of the image.
That's the meaning. Okay, formula?
V by U, sir.
V by U is for lens. For a mirror, it is minus V by U. But what is the, like by definition, what is the formula of magnification? Okay, generally, when we say magnification produced by a mirror or a lens, we mean height of image divided by height of object. Okay, that is the that is what we generally mean by magnification. That's okay. But when it comes to microscopes and telescopes, this is not the magnification we are interested in. See, one of you tell me, suppose there are two objects A and B. Fine. Let's say there are two cubes, A and B. A has dimensions 30 by 30 by 30, 30 centimeters, 30 centimeters, 30 centimeters. And B has dimensions 10 centimeters by 10 centimeters by 10 centimeters. You know which is the bigger cube, which is the smaller cube. But just because A has bigger dimensions doesn't mean it will always appear bigger than B. These are the dimensions of these cubes or boxes. Okay, one is a 30 by 30 by 30 box, the other is a 10 by 10 by 10 box. Suppose these two boxes are present in space somewhere. Just because A has bigger dimensions than B, these are their original dimensions, okay? Just because A has bigger dimensions than B, does it mean A will always appear bigger than B? That is my question. Rishi, what do you think?
Sir, can you repeat your question once?
I already repeated, okay. A and B are two cubes having these dimensions. Does that mean A always appears bigger than B?
Yes, sir, because its dimensions are bigger. But again, it depends on where it's placed. If like
So
A
you
is
you
placed,
consider all those factors and give your answer. Does A always appear bigger than B?
yes, sir.
Always.
No,
Then you,
no, not always, not always. So
not
if
always. Okay, okay, fine. Correct, correct. See, we know stars are huge. Okay, but when we look at stars, how do they appear? They appear like dots to us, very small. Fine. So just because an object is huge doesn't mean it appears huge to you. Okay. How you perceive the size of an object depends on the angle subtended by the endpoints of that object on your eye. So let's consider the eye and principal axis like this. Suppose there's an object in front of the eye, say here. Okay. You all must have observed this. A particular object itself, okay, the same object, when it's placed at different distances from your eye, its size appears different. When it's close to you, it appears bigger. When it's far from you, it appears smaller. Okay. Why that happens is because at a particular point on your eye, if you imagine the rays from the end points of the object incident, this ray and this ray, they subtend a certain angle here. Okay. Whether an object appears big to you or small to you depends on this angle. The same object, if it's taken far away from you, it subtends a smaller angle at a single point of your eye. Okay, that's why it appears smaller as it goes away from you. Okay, you can visualize it forms a smaller angle. It's not very difficult to imagine, right? So when it comes to a microscope or a telescope, the kind of magnification we are looking for is not linear magnification. We don't just want bigger images to be formed. We want bigger angles to be subtended on the eye. Okay. See, a bigger image doesn't always guarantee a bigger angle. For example, let's say this itself is the object, and you used some optical instrument, okay, and got a bigger image formed here. Now you are looking at it on your screen perpendicular to the scene, so you know which is bigger, which is smaller. Let's say this is the object, this is the image. Image is bigger than the object. It's a magnified image. Okay, it's clearly bigger. Okay. But if you look at the angle it subtends on the eye, it subtends a smaller angle than the object itself. Object is subtending a bigger angle. So if you see both of them, the object will appear bigger to you. Is this clear? Rishi and Pradyun, did you understand?
Yes, sir.
Even though the image is actually bigger, it will appear smaller to you because it is too far. Okay, or it subtends a smaller angle. So when it comes to magnification by a microscope or a telescope, or when it comes to actually magnifying something, what we are interested in is the angle subtended by that object or image on the eye. Okay, we call it as angular magnification. Fine. Suppose there's an object of height h that you are trying to see directly. Okay. Now, if you want to see something directly and as clearly as possible, you will bring it as close to your eye as possible, but you can't bring it too close. You can only bring it up to near point distance. So suppose the object is at near point distance. Fine. It's a small object. The height h is very small. In this diagram, we have shown a large height actually, but this is usually in millimeters. And d is approximately 25 centimeters. Okay. So there's a significant difference between h and d. H is a small height. It's a small object. Okay. Call this angle as theta. When you look at the object directly, let's call this angle theta naught. By placing it at the near point distance, the angle it subtends is theta naught. Now from this triangle itself, you can say tan theta naught is height of the object divided by distance from the eye. And because the height is very small, this angle is going to be a small angle. And for small angles, tan theta is approximately equal to theta itself. Therefore, the angle subtended on the eye is height of the object, original height of the object, divided by the near point distance. Okay. Now what we want is, we want the lens to form an image which subtends an angle bigger than this. Okay, fine. So is this point clear to all of you? How we derive this angle theta naught is equal to h by d? When we look at the object directly by keeping it at the near point distance, because that is when it would appear biggest to us, no? At the nearest distance of distinct vision, it appears biggest. Of course, if you bring it further closer to your eye, it will appear even bigger, but you can't see it clearly. We want to be able to see it clearly. So the nearest distance at which you can place it is the near point distance, capital D. And when you place it there, it subtends an angle h by d. Okay. Now we want an enlarged image of this. And we want to see how the rays from the image enter into the eye. Okay. Suppose the object is somewhere here and you place a converging lens, that is a convex lens, between the eye and the object. Let's assume the lens is placed very close to the eye. Or actually we can bring the eye into the picture later. We'll do that. Let's say the lens is placed here such that the object is within the focal length of the lens. If the object is within the focal length only, you can expect an enlarged upright image to form. So let this be the focal length. Okay, I'll draw the diagram quickly. Again, basic ray tracing. The other ray passes like this. In between these, there will be infinite other rays also. Okay, and this is where you get the image. Now bring the eye into the picture. What your eye sees is the image, because rays will enter into your eye as if they are coming from that position, from the image position. Your eye won't be able to see the object at all because light is not directly coming from that position into your eye. Okay, fine. Now to be able to clearly see this image, the image must be at least at a distance of near point distance. Okay, at least at capital D. Now, for convenience, or to take a simple case, what we assume is that the eye is very close to the magnifying glass. Okay, suppose the eye is very close to the convex lens. So whatever is the distance of the image from the lens, same is the distance of the image from the eye. We are ignoring this distance. We are neglecting this. That is how it is in your syllabus. Okay, whatever is the image distance from the lens, same is the image distance from the eye. Fine. And whatever angle the image subtends on the lens. Okay, see, this is one ray from the image. This is another ray from the image. The angle subtended is this now, theta. Whatever angle the image subtends on the lens, the same angle we assume is subtended by the image on the eye also. Okay, now you can understand the difference. When the eye looks at the object directly, it was subtending a small object. When the eye looks at this enlarged image, it is subtending a bigger angle. That is the kind of magnification we are looking for. This is what we call as angular magnification. And it is calculated as final angle subtended on the eye divided by initial angle subtended on the eye when we look at the object directly. Okay, the angle subtended on the eye when we look at it directly is h by d. That is known to us. What we now need is the angle subtended by the image on the eye. Is it clear till this point? what we are looking for and what kind of magnification we want and all. Pradhin is asking, is a similar concept used for parallax in determining the size of planets? No, this is not parallax actually. Okay, that we will discuss separately. Fine. Rishi, is this clear?
Yes, sir.
Fine. Now see, to be able to see this, what do you call, image clearly, the image should be at least at near point distance. Suppose the image is formed at near point distance. Okay. Or instead we can derive something general and take near point distance. No, let's derive something general. Actually, in NCERT textbook, they only take two cases. One case where the image is formed at near point distance, one case where it forms at infinity. Okay, why? If image forms at infinity, it is very convenient to look at for long durations because eye will be relaxed. If image forms at near point distance, there is a lot of strain on the eye, but it's the biggest image that you can get, best magnification that you can get. So best magnification or most relaxed view, those are the two cases they have considered. We'll derive something more general. Suppose the image is formed at a distance x and the object is at a distance d. Okay, I have to take both of them from the lens itself. Eye is very close to the lens. Okay, so object is at a distance d from the lens and image forms at a distance x from the lens. And the focal length of the lens, let's call it as f. Fine. Let's apply the lens formula. Lens formula is 1 by v minus 1 by u equal to 1 by f, right? Here, rays are going to the left side. Then anything on the left will be considered positive. Any distance on the right of the lens should be considered negative. So object distance, image distance should both be taken negative. That's fine. We'll do that. So substituting, we get 1 by image distance minus x minus 1 by object distance minus d is equal to 1 by f. Okay. Therefore, 1 by x becomes, I'm sending 1 by x that side, 1 by d minus 1 by f. And you can also say 1 by d becomes 1 by f plus 1 by x. That means d is equal to, okay, you take LCM and all, fx divided by f plus x. So if you want the image at a distance x, then the distance of the object should be d. So d is object distance, x is image distance, and you know that. Okay. And what we ultimately want is angular magnification, final angle subtended on the eye divided by initial angle. Now you look at this diagram, the final angle subtended on the eye, theta, is nothing but this height of the image divided by the distance x. You can write theta as capital H divided by x, but it's also equal to this height, small h, height of the object divided by d, small d, the object distance. Okay. So theta, the final angle subtended on the eye, is small h divided by small d. Theta naught, the initial angle subtended on the eye, when you looked at the object directly, is small h divided by capital D. You divide them, you get the magnification. This implies magnification, angular magnification produced by the simple microscope is capital D divided by small d. One of you quickly tell me what was small d in our derivation? What was small d? Small d is the distance where the object is placed to get the magnified image. Okay. Now, this might make it look like lesser the value of small d, greater the magnification. So you make small d tend to 0. Okay, but there is a problem. If small d tends to 0, what does it mean small d tending to 0? Object coming to the lens, object coming very close to the lens. If object comes very close to the lens, image also will come very close to the lens and you won't be able to see it clearly. Why? Because it will fall within the near point distance. You won't be able to see it. So you can't allow the object to come very close to the lens if you want to see the image clearly. So there's a certain minimum distance at which you can keep the object. The maximum distance at which you can keep the object is of course the focal length. In that case, image will form at infinity. You will be able to see it. Okay, but there's a certain minimum distance also. Fine. So that minimum distance where the object can be placed depends on the minimum distance where you want the image to form. And what is the minimum distance where we want the image to form? Near point distance. We don't want images closer than that. We cannot see them. Okay. We know d is equal to fx by f plus x. First case. Image forms at near point distance. If image forms at near point distance, small d becomes, or you can use this formula also, 1 by d is 1 by f plus 1 by x. Then 1 by d becomes 1 by f plus 1 by image distance. We want image to form at near point distance. So 1 by d becomes 1 by f plus 1 by capital D. Therefore, the angular magnification becomes, what's the formula for angular magnification? Capital D by small d. So capital D into 1 by small d you can write. That is capital D into 1 by f plus 1 by small d. Send capital D inside. This becomes 1 plus d by f. So if image forms at near point distance, this is the angular magnification that you get. 1 plus d by f. Okay. Let's go through this derivation once again. I mean, I'm sure you will be confused with this. First, we drew two ray diagrams. First one is when the eye looks at the object directly by keeping the object at the near point distance. When that object is seen directly by keeping it at the near point distance, the angle it subtends on the eye is h by d. Put it aside. Now, suppose the object is placed before a lens and the image is seen by the eye. That ray diagram also we have drawn. When the image is seen by the eye, the new angle subtended on the lens or the eye is theta, which is h divided by small d, where what is small d? The distance where the object is placed from the lens. That is not what the eye sees. Eye will see the image. Okay, but the angle subtended depends on where the object is placed. So we got that new angle as small h by small d, where d is the object distance. Fine. Therefore, the magnification, angular magnification, becomes h by small d, that is the new angle subtended on the eye, divided by h by capital D, the original angle subtended on the eye. So this becomes capital D by small d, where small d is the object distance. Now, by looking at this formula, you may think that smaller the object distance, greater the magnification, so make object distance tend to 0. But if object distance tends to 0, image distance also will tend to 0, and it will form within the near point distance. We won't be able to see it. Okay, so there is a certain minimum object distance that you need to maintain. And what is that minimum object distance? We use the lens formula here. We got a relation between object distance and image distance. The minimum object distance is dictated by the minimum image distance. And where do we want the image to form? Minimum at near point distance, capital D. So I use this formula to get small d corresponding to capital D. Small d corresponding to capital D is related like this. That I substitute here. and we get the magnification as 1 plus d by f. So if the image forms at the near point distance, the magnification is 1 plus d by f. Rishi, is this clear?
Yes, sir.
Okay. Second case. Okay, this is the last thing that we'll discuss for today. Suppose image forms at infinity. Rishi, you tell me, for the image to form at infinity, where should an object be placed?
At the focus, sir.
At the focus. So d must be equal to the focal length of the lens. And if small d is equal to focal length, then the angular magnification becomes capital D by small d. That becomes capital D divided by f. So this is the magnification that you get when image forms at infinity, d by f, angular magnification. When it forms at near point distance, you get 1 plus d by f. When it forms at infinity, you get d by f. If it forms somewhere in between those two, the magnification also will lie between these two values. Okay. So what's the difference? 1 plus d by f is the best magnification that you can get, but there will be a strain on the eye. D by f is the least magnification we can get, but it is most comfortable for viewing. Fine. Next class we'll solve some problems based on this. You'll understand better, and we'll also discuss image formation by a telescope. Now, what you see here is the ray diagram in case of image formation by a converging lens, a lens which has positive focal length, when the object is within the focal length. This is the focus. The object O is between the lens and the focus. Okay, you get an image beyond the focus. It will be a virtual image. Magnified linear magnification will be there and all. Okay. Assume the object is at a distance d, small d from the lens. D is the magnitude of the distance. Assume the image is formed at a distance x from the lens, and focal length is f. Okay. We had discussed in the last class, but do this once again. Rishi, apply the lens formula and derive the relation between these three: small d, x, and f. Or indirectly, what I'm asking you to do is just substitute these values in the lens formula properly. That's all. Try. Let's see. Tell me the lens formula first.
1 by V minus 1 by U is equal to 1 by F.
Okay. And see, we use this same formula for all cases of image formation by lenses, right? Yes or no?
Yes, sir.
Yeah. If you want to use this in every case, you will have to substitute V, U, and F by following the rules of sign convention. Now, in the given diagram.
Sir, 1 minute, sir. Just give me one more. I just want to check.
Okay. Okay. Try. Okay. See, D and X here are just distances, magnitudes. Fine. First, you can see on which side the object is, which way the rays are traveling. And the positive negative also have been marked in the diagram. Okay. Any distance to the left of the lens is taken positive. Any distance to the right is taken negative. So tell me, when you substitute the object distance D in the lens formula, should you take it as plus D or minus D?
Sir, minus.
Correct. It's on the negative side. So object distance is minus D. Fine. Image distance X. Will you substitute as plus X or minus X?
Minus.
Minus. It's also on the negative side. Correct. And this is a converging lens. Focal length is positive. That you have to take as it is. Okay. Fine. So you get this minus and minus cancel. It becomes a plus. You get 1 by D is equal to, what did you say?
1 by x minus 1 by f.
Why will it be minus? See, the x has a negative sign on the left hand side. When it goes to the right side, it becomes positive. So what you get is 1 by f plus 1 by x, no?
Sir, but focal length is negative only, no? Because it's
No,
on.
focal length is positive.
Oh,
See, rays are traveling to the left now, and this is a converging lens. For a converging lens, focal length will be positive. You can't change that. Okay,
okay, sir.
this is the focus actually. It's on the positive side.
Oh, understood, sir. Understood.
The f on the right side was just shown. I mean, was just marked to show that the object is within the focal length on that side, but the actual focus is on this side because rays are traveling this way. Okay.
Sir, but
Huh.
sometimes in situations like that, when do we recognize what the focal length is, or do we just get to know it?
In the problem, they will give you the focal length.
Oh, okay, sir. That makes
Huh. Now, which way are the rays traveling in this diagram? To
from
the
the
right.
left to the
Huh.
right.
No, they're going from the right to the left. No, the arrows are pointing to the
Yeah,
left.
yeah. Yes, sir. Yes, sir.
Huh. So left side is positive, and converging lens has a positive focal length. So we take the focus on this side, left side. Had the rays been incident from the left side, passing to the right side, then we would have taken the focus on the other side. Okay, so where exactly the focus is depends on the direction in which the rays are traveling. Okay, so you get 1 by d is 1 by f plus 1 by x. That means 1 by d is equal to, if you take the LCM, f plus x divided by fx. And okay, you can keep it as it is. This is what we are looking for. So what is d in this formula? What is small
Image
d?
distance.
No. Small d is the object distance.
Object distance. Yes, object distance.
Okay, and x is the image distance. Okay, so based on where you want the image to form, you can choose the object distance by using this formula. Fine. Okay. Can you quickly tell me what is angular magnification? We had discussed about this in the last class. Angular magnification produced by a microscope. Okay, let's revise
Sir,
this once again. Yeah, tell me.
and the magnification is the angle of the image by the angle of the object, right?
No. Okay, this is where most students make a mistake. Linear magnification is height of image by height of object. Okay, in a given situation. But when it comes to microscopes and telescopes, you should understand what is the magnification we look for. This magnification is not what we want. We don't just want to form an enlarged image. Okay, that's not what we are looking for. Why do you use a microscope or a telescope? Microscope you will use because the object is too small. With your naked eye, you are not able to see it clearly. Okay, so when seen through the instrument, it should appear bigger than when you see with the naked eye. So in case of microscopes and telescopes, magnification is the ratio of angles subtended when you see through the instrument and when you see directly. Okay, it's not object and image when seen through the lens. It's not like that. You see through the lens, the image will subtend an angle on your eye, which is the theta shown in this diagram. You don't use the lens, look at the object directly. Okay, that also we have discussed yesterday. I'll just show you the diagram. Yeah, when you look at the object directly, this is what it looks like. Okay, it subtends a certain angle on your eye. We want to make that angle bigger. Okay, by looking through the lens or looking through the instrument. So what is angular magnification? The angle subtended by the image when you look through the instrument divided by angle subtended by the object when you see it directly. That you have to say. Okay, so the answer you gave, angle subtended by image divided by angle subtended by object, is only half correct. You should say that it's the angle subtended by image when seen through the instrument divided by the angle subtended by the object when seen directly. Different cases. Okay. Now, when you look at the object directly, what angle does it subtend on the eye? This much, theta naught. The angle subtended on the eye when the object is seen directly is h divided by capital D, where h is the original height of the object, capital D is the near point distance. Rishi, are you clear with this or not?
Yes, sir. Understood.
Ha. It's a small object, no? So you'll obviously keep it as close as possible and see. So you are keeping it at the near point distance. That is
So
when it.
that's like the optimum angle where everything is clear. So lesser is not clear and more is also not clear.
No, 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 no. Near point distance is the distance, shortest distance at which you start seeing things clearly. Okay, it's not
Oh,
about the angle. It's the shortest distance at which you start seeing things clearly. Like you can try this. You take your finger too close to your eye and you try to like focus on it. You won't be able to get a clear image. But when you start moving your finger away from your eye at one minimum distance, you will be able to see it clearly.
yes, sir. Yes.
That distance is what we are talking about. Okay. On average for human beings, it is about 25 centimeters. Okay, so when you see the object directly, the angle subtended on the eye is small h divided by d, where small h is the height of the object, d is the near point distance. Is this clear?
Yes, sir.
Now look at the other diagram. When you look at the object through the instrument, through the simple microscope, see what is happening. You won't be able to see the object. You'll be seeing the image anyway. Rays will appear to be coming from this point. Fine. So what you see is the image, and the image is subtending an angle theta here. Do you notice this angle? Now you can say that tan theta is opposite divided by adjacent. You can say it is capital H divided by X. You can also say it is small h divided by small d. Yes or no?
Yes, sir.
We can? Okay. So the new angle subtended on the eye when seen through the simple microscope is small h divided by small d. But when we look at the object with naked eye, it was small h divided by capital D. Therefore, the magnification produced by the simple microscope, the angular magnification, is the new angle divided by the original angle. New angle is small h divided by small d. Original angle is small h divided by capital D. Therefore, magnification simply becomes capital D divided by small d, which is, or which can be written as capital D into 1 by d. And today itself we derived 1 by d is nothing but 1 by f plus 1 by x. Clear? Any doubt in this?
Yes.
Fine. So the amount of magnification produced by the microscope depends on where you make the image form. Okay, this is the image distance, right? Capital D is the near point distance, which is fixed. F is the focal length of the lens, that is also fixed. Okay, but you have the liberty to place the object wherever you want and make the image form wherever you want. Okay, at different distances. Wherever you want means not completely. Object has to be within the focal length. Image will form outside the focal length. Okay, but outside the focal length, wherever you want to make it form, you can make it form. Okay, so we have the liberty to adjust the image distance. And if you can do that, you can change the magnification. You will get different magnifications for different image distances. Is it clear?
Yes, sir.
Now, Rishi, you tell me, what is the nearest distance or the shortest distance at which you can allow the image to form so that you'll be able to see it clearly?
25.
Capital D, that near point distance. Okay. So you can see that in the magnification formula, image distance is in the denominator. So smaller this value, greater the magnification. Okay. So if you make the image form At the closest possible distance at which you can see it clearly, you will get the best possible magnification. So first case, for best magnification, x must be the least, because x is in the denominator. No, smaller the denominator, greater the value. Okay. So for best magnification, x should be equal to capital D. Means you should allow the image to form at the near point distance. Now if x is capital D, then the magnification becomes D into 1 by f plus 1 by capital D. You send the capital D inside, it becomes 1 plus D by f. Is this clear?
Yes, sir.
Okay. So where should the image form for the best magnification? Where means at what distance should you allow the image to form to get best magnification?
At the most minimal, but is that 0?
Can you see objects which are at 0 distance from your eye?
No.
So where should it be allowed to form? What's the nearest distance at which you can see the object, see the image?
25.
Capital D. Okay, so that is what I was asking. For best magnification, image should form at capital D, the near point distance, and in that case, the best magnification you get is this much. Is it clear?
Yes, sir.
Okay. But there's a problem with making the image form so close. Now, usually also you must be knowing, like for people who work on computers for long durations, what do they suggest to do for relaxing their eye?
They're moving of their eyes. Like
Moving of eyes is one thing, and another thing,
blinking.
blinking anyway, yeah, that they have to do. In terms of seeing, okay, see what they suggest is, they suggest the person to look at a faraway object for some 5 minutes or so in every half an hour. Okay, because it is comfortable for our eyes to look at faraway objects than to look at objects which are at the nearest possible distance at which we can see. Okay. The farther the more, the farther the object or the image is, the more comfortable it is for us to look at it. I'm not talking about clarity. Okay, if something goes very far away from you, you can't see the details that well, but for your eye, it will be more relaxed. Just to identify whether there's something there or not, you can. Yes or no? Okay, looking at an object for long durations by keeping it at the shortest possible distance is stressful for the eye. Okay, so you get the best magnification when the image is formed at the near point distance. Closer the image, better the magnification. But closer the image, greater the stress on your eye to look at it for long durations. So what we do is, we take another case for most comfortable viewing. Okay, for most comfortable viewing, image should form at infinity. In that case, what will the angular magnification of the simple microscope be? D into 1 by f plus 1 by x. X tends to infinity. If x tends to infinity, that term becomes 0. You'll be getting d by f. Okay, so for most comfortable viewing, the image should form at infinity. And in that case, the magnification you get is d by f. You still get significant magnification. Okay, angular magnification. You will be able to see it in quite a bit of detail. You can see that the difference between this magnification and this magnification, the best and the worst, is only 1 unit. Okay, for example, you know that the average near point distance is 25 centimeters. Assume you use a lens whose focal length is 5 centimeters. Then d by f becomes 5. That means the best magnification you can get is 1 plus 5, that is 6 times. And the worst magnification you can get is 5 times. So if you go for comfortable viewing, you will still be getting a significant amount of magnification. Rishi, is this clear or not?
Yes, sir.
Okay. Usually in your textbook, they discuss only these two cases, where image is formed at the near point distance or where image is formed at infinity. But you can make the image form wherever you want between these two extremes. And in those cases, the magnification will change. Best case magnification is 1 plus d by f. Worst case magnification is d by f. In other cases, you will get magnification between these two values. Okay. So that is the idea behind the working of a simple microscope or a magnifying glass. Tell me, for a simple microscope to perform its function, at what maximum distance can you allow the object to be placed?
Can you repeat your question?
For a simple microscope to work as intended, at what maximum distance can the object be placed from it?
Sir, is it X?
X is the distance where the image is forming.
D, small d.
Small d is the distance where we have placed the object. I'm asking you, up to what maximum value can small d be increased?
Till infinity.
No. See, this kind of image formation is possible by a converging lens only if object is placed within the focal length. You can only allow it to increase up to f, not beyond that. Okay, object must lie within this range. Okay. That's why I repeatedly ask you to draw the ray diagrams in all cases. Only when object is placed within the focal length, you can get an enlarged image like this behind the lens. Once the object crosses focus, image will form on the other side. Then you can't see it clearly. Okay, so see, set aside some time and work on ray diagrams by mirrors and lenses. Okay, in all possible cases, you should be very comfortable imagining the image formation. Right. So this is what a simple microscope does. Basically, it has one converging lens and it can produce magnifications ranging from d by f to 1 plus d by f.